Hello everyone, we're going to do our lecture on gases now. So this is a follow-up to our states of matter lecture that we had a couple nights ago. Okay, so you'll remember a couple nights ago when we did the lecture on states of matter, we mentioned the kinetic theory. And now we want to sort of remind you about that and take a little more specific conversation about the properties of gases with respect to kinetic theory. All right, so the kinetic theory, this is the theory that all particles, atoms, or molecules are in constant motion, and that motion is defined as their kinetic energy. All right, um, and the kinetic energy of a system is directly related to the temperature. So the higher the temperature of a system, the more kinetic energy it has. All right, so with respect to gases, the kinetic theory assumes that the volume of a gas particle is insignificant. In other words, what that means is that if you've got a container full of gas particles, um, the space inside the container is mostly empty because the gas particles are tiny compared to the volume of the space that they are contained in. So the volume of the gas particle is insignificant. That's one of the assumptions of the kinetic theory with respect to gases. Another, it's kind of the same thing, there is a lot of space between gas particles. So the particles are not close to one another. And one ramification of that is that the gas particles don't attract or repel each other. They don't feel intermolecular forces because they're very small. The particles are very far apart, and they have a very tiny volume. And then another assumption is that the gas particles move constantly and rapidly. So that idea of have you ever seen when they do the number drawing for like the lotto? They have this big plastic drum, and inside the drum are a bunch of ping pong balls, and on the ping pong balls are painted numbers, and there's like air that blows into this big drum, and so the ping pong balls are spinning around, flying around inside the drum. Well, that's kind of how gas particles are inside a container. So if you've ever seen that, you'll know what I'm talking about. And if you've never seen that, you're kind of going, what? And so let's just drop it and move on. Okay, so all of these assumptions about the kinetic theory assume the kinetic theory assumes all these things are true about gas particles, and that would make we have a term for that, and that's called an ideal gas. An ideal gas is one that meets all of those characteristics described by the kinetic theory. Of course, it's theoretical. There isn't actually any gas that does that. So let's do a quick comparison between ideal gases and a real gas. Well, an ideal gas, the particle has no volume, or in other words, it's insignificant, like we said. A real gas, of course, there is an actual volume associated with the molecule. It's small, but it's real. Um, Ideal gases aren't attracted, the particles do not attract or repel one another. That's one of the tenets or one of the assumptions of the theory we just spoke about. And of course, for real gases, there are some small but real intermolecular forces between the particles. So the ideal gas has no such attraction between particles. Real gases, there is actually a little bit of attraction. Ideal gases can't be turned into liquids or solids. No matter how much pressure you put them under, no matter what you change the temperature to, they can't be liquefied or solidified. And of course, that's not true for real gases. They can be turned into liquids or solids. So this is just a quick comparison between what the ideal gases are like. Well, they don't exist, of course, but this hypothetical ideal gas, what it would be like, compared to what a real gas is like. These differences might seem like they're really important, but but in reality, they're not that significant of a difference. So you can use the theory of kinetic. Sorry, you can use the kinetic theory of gases to make some predictions about how gases behave and apply. And even though they're designed for ideal gases, they work for real gases. All right. So when do real gases act like ideal gases? So temperatures have to either be high. Well, actually, the temperature has to be high and the pressure has to be low. And if that's true, then a real gas will act like an ideal gas. Now, let's think about why that's true. Temperatures are high and pressures are low. Think about the characteristics of an ideal gas that we just mentioned. Why might high temperature and low pressure make a real gas sort of act like an ideal gas? Well, High temperature means there's a lot of kinetic energy, so the particles are moving really quickly and randomly, um, and the faster and the more quickly they are moving, the more their momentum is conserved between collisions, so there's less loss. And so that's what high temperature means. So a real gas acts like an ideal gas when the temperature is high. The low pressure part of it means the particles don't hit the container or each other very often. So they don't feel attraction or repulsion forces. And because, of course, for attractive or repulsive forces to act, the two particles have to be close to each other. Low pressure means the particles are far apart. There aren't very many particles in the space, and so they don't really interact with each other very much. So if you've got a situation of high temperature and low pressure, um, that's a condition where real gases can act like an ideal gas, even though, like I said, the ideal gas is not a real thing, it's hypothetical. All right? So we need to discuss the variables that describe a gas or the characteristics of a gas, and these kind of came up in the other lecture, but we're going to revisit them here just to make sure you remember. One of the characteristics that describe a gas is the pressure, and like I mentioned in the previous lecture, there are a number of ways to measure pressure. You need to be able to convert between different measurements of pressure, like atmosphere, millimeters, mercury, and kilopascals, and torr was the other example. You need to be able to interconvert between pressure measurements. Um, Another variable that describes a gas is the volume, usually measured in liters. You might see it in milliliters or deciliters or something like that, but um, liter is the standard measurement for volume. And then temperature is important. So temperature is another Temperature is another characteristic of a gas. And when we're talking about gases, you always want to use Kelvin. We talked about the Kelvin scale in the previous slide. In the previous presentation. And then, of course, the amount of the gas matters. So you can measure that most often in the number of moles, or if you're given the amount of gas in grams, you could convert it to moles using the molar mass. So these are the types of variables that you need to describe a gas. We're going to now do a couple of quick thought experiments before we get to the calculations part. So here we have a container. A sealed container, and inside that container is some oxygen. There are oxygen molecules in here. That's the little black dots. And the little lines that come off of them are supposed to show that they're moving around, all right, because the gas is constantly moving, right? So the pressure in this vessel, in this piston, is 0.359 atmospheres. That's just a starting point, and the volume is 4 liters. Okay, so let's just kind of keep that in mind, and let's do some thought experiments about what happens if we change the temperature on this container. All right, so think about the gas molecules that are moving around inside this container. They have a certain amount of kinetic energy. If we increase the temperature, what will that change? Well, it will change the kinetic energy. It will increase the kinetic energy of the system, which means the molecules are moving faster. And when they're moving faster, they're banging into each other and into the sides of the container. Here, into the sides of the container, those collisions between gas molecules and the sides of the container happen more frequently, which means the pressure will increase. So if you increase the temperature, the pressure may increase. Or if, let's assume, what if this bar is not fixed? What if this size of this vessel can change and this bar can move upwards? Well, if you increase the temperature, then the lid basically of this container could slide upwards, and that would change the volume of this container. All right? So when temperature goes up, pressure or volume may go up. What happens if we decrease the volume of the container? So again, what if this bar, this top of the container, can slide downward to make the volume of the container smaller? What do you think would happen? Well, either the pressure may increase because you've got the same number of molecules still moving around, but it's a smaller space, so that's more pressure. Or the temperature may go up, just the opposite of, just like what we saw previously. So the if you decrease the volume of this container, you may increase the kinetic energy of the molecules inside, and their temperature may go up. What happens if we increase the pressure? Now that one's a little harder to imagine with pressure here. I don't know why the computer keeps doing that. I apologize. One way to increase the pressure would be to put more molecules in here. What if we increase the pressure? Or of course you could move this. The temperature may go up, or the volume may decrease. So those are the things that could change. So what I want, the purpose of this thought experiment is to get you to kind of think about the characteristics of gases and how they relate to one another. All right? So think about that. And now we can look at what are called the gas laws. So chemists in the past, particularly in the 1800s, did a lot of research about gases and how gases work and how the characteristics of a gas relate to one another. There were three chemists in particular who came up with laws or equations that describe and connect pressure, temperature, and volume. There is, oh geez Louise, there is Boyle's law, Charles' law, and Gay-Lussac's law. And you can see, and I don't want you to spend a lot of time on this because there's a better one, but hang on. Boyle's law connects pressure and volume. Charles' law connects volume and temperature. And Gay-Lussac's law connects temperature to pressure. All right? So that would be a lot to remember and kind of a hassle to deal with because there are three of them. So instead, we have created a combined gas law. This is the one that you want to remember. This is the one you want to write down. It's called the combined gas law, and it connects pressure, volume, and temperature to pressure, volume, and temperature. Now, just a quick explanation of what we're looking at here. The subscripts 1 or 2 describe initial and final conditions. So you have a starting set of conditions and an ending set of conditions. And the pressure times the volume divided by the temperature at the starting point has to be the same as the pressure, volume, and temperature combination at the end. All right, so these, in other words, changes in one thing produce, in one characteristics, like change in a pressure, will produce a change in volume or temperature so that this remains constant. So P1 V1 over T1 equals P2 V2 over T2. This is called the combined gas law. This is the one that you want to remember. Don't worry about details of Gay-Lussac and Boyle and so on. Just use the combined gas law for all kinds of gas law problems. This will allow us to predict what happens to a gas if we change one of the conditions. If the temperature changes, what will happen to the pressure and temperature? The pressure and volume. Okay, so let's do a little. Let's do a little practice problem. So we have a practice problem here. A gas with a volume of 4 liters at 90 kilopascals, that's the pressure, expands until the pressure drops to 20 kilopascals. What is the new volume if the temperature remains constant? Okay, so again, this is an exercise in reading the question and pulling out information. We need to find initial temperature, pressure, and volume, and final temperature, pressure, and volume. That's how we use the combined gas law. So let's identify what we know first. All right, so the initial volume, here's the gas with a volume of 4 liters. That's the starting point. So the initial volume, V1, is 4 liters. And the initial pressure is 90 kilopascals. All right, and then some kind of change happens. Expands, it says. So there's some kind of change. Now the pressure drops to 20 kilopascals. That means that the secondary pressure, the final pressure, P2, is 20. All right, we're trying to find the new volume, so we don't know what V2 is. And we're told that the temperature remains the same. T1 and T2 are the same. They don't change. So now we want to use our combined gas law and solve for what we don't know. And where'd it go? There we go. So we start with P1 times V1 over T1 equals P2. Oops, that slid. I apologize for that. This T2 is supposed to be over here. P2 V2 over T2. That's the starting point for the combined gas law. You need to rearrange that algebraically to solve for what we don't know, which is V2. It's true that we don't have numbers for T1 and T2, but since the temperature stays the same, the temperature part drops out of the equation. So to solve for V2, you get P1 V1 T2 over T1 times P2. I want you to try to work that out on your notes right now because I kind of blew through that quickly. My assumption is that you know how to do algebraic rearrangements, but just take a minute to practice it. But what you should get is to solve for V2, you get P1 V1 times T2 all divided by T1 times P2. If we then substitute, now look what I did with this. Since T1 and T2 are equal to each other, I just put T1 on the top and on the bottom. I substituted. Since T1 and T2 are the same, they just drop out. They cancel each other out of the equation. If you do this math, you get 18 liters. So in other words, the answer to this question, the new volume, is now 18 liters. Okay? That may have gone by kind of fast, so take a look at it. Make sure you understand it. Let's try one more. Okay, a gas has a volume of 3 times 10 to the second milliliters. That's, of course, 300 milliliters at 150 degrees C. Oops, we need Kelvin. And it's heated, so that means the temperature is going to change, until the volume becomes 6 times 10 to the 2 milliliters, or 600 milliliters. What is the new temperature? If the pressure, if the pressure remains constant at 1 atmosphere during the heating. All right, so we're going to use the same process as before. We're going to identify what we know and then solve that combined gas law equation for what we don't know. We do have to convert our temperature to Kelvin. It's important to have Kelvin for gas law equations. So, So T1 is 150 degrees, and if you convert that to Kelvin, it's 423 degrees. Okay. We know that the pressure remains constant, so P1 equals P2. We know that the initial volume is 3 times 10 to the second milliliters, and the second volume, the final volume, is 6 times 10 to the second milliliters. And now we solve for what we don't know, which is what we're trying to find, T2, and substitute. Oh my goodness. T2 is T1 times P2 V2 all divided by P1 V1. And again, I want you to take a minute to kind of convince yourself that that's the truth. And then substitute what we know in there. And I didn't show you the substitution because I'm assuming you're going to do it in your notes. So when you do the math, you get, oh gosh, I will have to figure out why that's happening. I don't like Windows 8, just so you know. So when you do the math here, you get T2 equals 846 Kelvin. So that's the new temperature. Now you could convert this back to centigrade. It doesn't actually ask you to do that, so you could leave your answer in Kelvin, or you could convert it back to centigrade by subtracting 273. Okay, so that's our couple of examples of how to use the ideal gas law in calculations of conditions of a gas. We have to touch on one more aspect of gas law characteristics, and that's about the components of a gas. So we've been talking about gases up to this point as if there was just one type of gas in the container, like we had a container with oxygen gas in it, for example, in that picture I used earlier. But what if there was a combination of gases or a mixture of gases inside a container? If you've got a mixture of gases, we use something called Dalton's law of partial pressure. This is the same Dalton that gave us some of our atomic theory. So same dude. Okay, so he realized that if you've got a mixture of gases, the pressure of the whole gas is made up of the contributions of the to pressure from each of the individual gases. So each gas in the mixture has a partial pressure. And if you add up those partial pressures, you get the total pressure. So the total pressure, P sub T, is equal to the partial pressure of the first gas plus the partial pressure of the second gas plus the partial pressure of the third gas, and so on, for however many gases happen to be in the mixture. Okay, so the total just equals the sum of the parts. Let's take a look at an example of that because I think it helps. So air, the stuff that we're breathing, is made up mostly of oxygen and nitrogen, carbon dioxide. There are some other things, of course, but let's assume we had a sample that only had carbon dioxide, oxygen, and nitrogen in it. And if the total pressure of that sample is 1 atmosphere, we could calculate the partial pressures if we were given enough information. So let's assume that the partial pressure of carbon dioxide and nitrogen are 0.285 torr and 593 torr respectively. It's a pretty big difference, but here's another thing, this notation. So the P is pressure, and the subscript CO2 means the partial pressure of carbon dioxide, partial pressure of nitrogen. Okay, so we're given the partial pressures of 2 of the 3 components, and we want to find the third using Dalton's law of partial pressure. Okay, so we know that the sample is at 1 atmosphere, and that means that's the total pressure, P sub T, from that earlier slide. So let's convert atmospheres to torrs because the measurements given in the question are in torr. So we have PCO2 is 0.285 torr, and partial pressure of N2 is 593.525 torr. All right. So we remember from Dalton's law that the total pressure equals the sum of the partial pressures. So the total pressure, 760 torr, equals the sum of the partial pressures, 593.525 torr plus 0.285 torr plus whatever contribution oxygen is making. So the partial pressure of oxygen is just, we do the math there, and you should get 166.19 torr. All right? So kind of a simple concept, but with kind of more complicated language around it or terminology around it. So don't get hung up on the partial pressure terminology. Doing a problem like this, you'll see these on tests and so on. There's an example of a partial pressure question. All right. So just to quickly summarize the things that we covered in this lecture, because these are the important pieces that I want you to take away. Yikes! You now know that I don't like Windows 8. You also know about the kinetic theory of gases and the assumptions that you have to make for it. You know about ideal versus real gases, and we talked about the characteristics that describe a gas. We can now predict changes to one characteristic when the others change, like that thought experiment with the little picture that I had. What happens to the pressure if something changes? All right, remember that? And then we can actually calculate changes to one characteristics when the other change. That was the combined gas law. P1 V1 over T1 equals P2 V2 over T2. And then finally, you know how to calculate partial pressures. All right, that's using Dalton's law of partial pressures. That's it. There is no gases part 2 because I changed the slides deck, but I just didn't remove this slide. So we are done. Thank you very much.